So let's take a look at a function. Let's maybe do f of x equals x minus 1 over 3 minus x. And this is a rational function, right? Already reduced. Who can tell me the domain here?
3. X can't equal 3.
Nice. What about range?
I think it's y can equals -1.
Nice. Nice. Now, remember, we can find that range very easily by getting, if this turns out to be 1-to-1, and it is, we can find the inverse function and get the domain of that. We have easy domain rules, right? Our easy domain rules are what? And you can chat it if you don't want to say anything. What are our domain rules? What are the things we can't do at this point in our mathematical careers?
Divide by 0.
Divide by 0, or take an even root of
a negative number.
A negative number. Thank you, Joe. So we're adding a domain rule today. Okay, we're adding a new domain rule today for our log functions. So we'll double check this when we get our inverse. We want to we can tell quite a few things about this. What's the horizontal asymptote here? What's our horizontal asymptote? What's the mother function of upstairs? Is x. What's the mother function downstairs?
X.
Negative x.
Negative x.
Negative x. And there's that -1. There's that y related to a height of -1, right, in my range. What about a vertical asymptote here?
3.
Yes. Easy. So you can see really how these things are related. I can have, remember, a function can cross my horizontal asymptote in the short run. So it's not always going to happen this way, where it's not crossing. And if you look back at our first look at rational functions, you'll see cases like that. What else do I know? How about x-intercept?
One.
Yes. So I want it as a point. I have 1 comma what?
1,0.
Nice. Nice. And what about y-intercept?
0, -1/3.
Yes, 0, -1/3. Everyone, yes, we're agreeing?
Yeah.
Nice. Grace, thank you. Diego. So I'm pretty much ready to graph this. I want to do short run behavior as well, right? So I've got my x and y axis here, right? And of course, remember, you're going to use your calculator to verify that you've got things right, but you're going to communicate to me that you understand this without the calculator on the paper, right? So at x equals 3, I've got a vertical asymptote. The function will never cross the vertical asymptote, right? The graph will never cross that. Horizontal asymptote at positive 3. I think it's a -3. And then at -1, we've got our horizontal asymptote. It's almost like I've created a new origin, right? The new place where the axes cross here, right? And I've shifted it over, right? And so I have some points. I have 1, 0, right? And 0 -1/3, which is kind of hinting at that the function has to be up here and over here, right? Do you see that? But are you seeing? Because once I get those points, I kind of know which quadrant the piece of my function is in, right? The piece of this rational function.
Right, I see.
Yeah. So that's right. That's kind of cheating our short run behavior piece. Where do I want to do this short run at? What x value am I interested in this short run behavior?
You could do 1.
Well, one,
0.
yeah, but 1, I definitely know how it's behaving. It's got a height, it's 1,
Right.
right? So, oh, 3, yeah, Alan, thank you. So f of 3 kind of looks like 3 minus 1 over 3 minus x. I cannot put that 3 in the denominator. I'll get a 0. But I can put it in the numerator, and I get a 2 over 3 minus x. And I'm saying that I can really see the mother function there. That's really behaving like negative 1 over x, right? I can see the mother function overall there. And remember what negative 1 over x looks like, right? Bottom right, top left. And that's what I have in my function. Anybody understanding that a little more as we do them more and more?
Yeah, it makes more sense.
Michelle,
Definitely makes
Grace,
a little more sense.
nice.
Yeah.
Angel, nice. Brandon, nice. So now what do we know about this function? Seeing this graph, using our methods from from our rational function chapter 4, we now see that what's true about this graph. What's true about this function from the graph? I want to get my crickets going. What's true?
That the function is 1 to 1.
1 to 1. All right, and how do we know it's 1 to 1?
Horizontal line test.
Horizontal line test. We're not right for every unique height. There's 1 and only 1x. So by the graph, we know f of x is 1 to 1. But we want to prove it, right? So prove f of x is 1 to 1. What's our process?
If A has to be equal to FB.
Good. Pick what seems to be two different inputs and show that they're actually the same input. If I can show that f of A equals f of B, then A equals B, I know it's 1 to 1. It's what is it saying on the left here? I've repeated y values. I've got the same y value. If I have the same y value, it has to be the same x value, right? Equal y's must give. I hate that Teams announcement stuff. So what do we got? I forget my function already. X minus 1 over, yeah, so A minus 1 over 3 minus A equals B minus 1 over 3 minus B. I want to show, right? Show that this implies A equals B. Okay, so what do I do? What do I do with this green box? Someone help me.
Cross multiply.
Cross multiply. So at this point, you're all racing me. You're not copying down what I'm doing. You're doing the work, right? You're not just copying me. Right now, you know how to cross multiply this, right? So I get A minus 1 times 3 minus B equals B minus 1. That quantity times 3 quantity 3 minus A. We don't like this secretiveness here going on, right? There's associations going on that we want to break up, right? So what are we going to do?
Factor.
Factor if I could. It is actually kind of in factored form now, right? So I want to undo that.
Foil.
Yeah, distribute, right? So, and I've got 3a minus ab minus 3 plus b, right? And again, you don't have to do your distributing the way I do it, right? So you don't have to copy the arithmetic I do the way right? You do it your way. As long as you're not making a mistake, I don't care how you're doing it, right? So now things will cancel here, right? Like my ABs will go away, the negative 3's will go away, and I'm not trying to do too much, I'm just trying to rewrite. And now I want to gather all my A terms on one side and all the B terms on the other, and I'm trying to minimize the number of negative signs. Not much I can do in this case. So I get 2a equals 2b, or divide by 2, I get a equals b. So f is 1 to 1. Beautiful. So now what? What does it mean when a function is 1 to 1? What's special about that?
It has an inverse that is also a function.
Nice. Nice. So once I know a function is 1 to 1, right? I know that an inverse function exists. So that's what I want to do. I want to find that inverse function. So let me just go to a new page. Is it okay if I go to a new page here?
Yeah.
Fine by me.
Anybody need a second, a minute? Four, 8, 12, 16, 18. Only missing 3 students. Not bad. Not good. Okay, so we know, right? I'm going to find the inverse now. So f is x minus 1 over 3 minus x is 1 to 1. So f inverse, right, or g exists. I just like to call it g because it saves me a little time, right? No one ever says, what up, f inverse? We would say, what up, g? It's just quicker. So how do I find it?
You gotta like switch the x into y.
Okay, so first I'm gonna go back to my y notation instead of the f of x notation, right? And then solve for
Y. Or
so
X.
yeah, so you could switch and solve for y, or you could just solve for x and then switch. Either way, right? It doesn't matter. Same result. So we're going to cross multiply here, right? Then we're going to distribute. And now I want to isolate my x terms with the least number of negative signs. So notice if I moved my x's to the left side, everything on the left side would be negative. So I'm thinking the other way. I want to go the other way, right? So I'm going to bring the 1 over to the left and the xy over to the right. Everybody with me there? When I move a whole term over, it changes sign. So I'm trying to just minimize, thanks Grace, I'm trying to minimize the number of negatives. It's not wrong to have a whole bunch of negatives, but then you've got extra step to simplify. And I would say do it both ways and you'll see what I mean, right? Do this one over and move your x's to the other side and you'll see what I mean, okay? So now on the right we can factor. And finally solve for x, right? X is equal to 3y plus 1 over y plus 1. And I just switch my orders, just based on how we write polynomials, that type of thing. So now is everybody okay here with me?
Yes.
Not quite. I'm a little confused on the last step.
Okay, so step.
Oh wait, no, I got it.
Step 4 to 5. Step 4 to 5. Yeah, that dividing by. And I skip all of that algebra, right? We used to do stuff like this in probably our algebra 1 class. I don't put any of that in there, but right, if you ever don't see it, right, just let me know. Okay, nice. So this is y now. This is my inverse function, 3x plus 1 over x plus 1. And I'm going to call that f inverse of x. And of course, my preference is just to call it g. So so there's my inverse function. How can I do a quick double check that maybe I have it right. What's my process?
Just get any number that could fit the domain.
Beautiful. So pick some number in the domain of f, get the result, get the output. Then take that output and put it into G and see if our x's and y's are switching, right? Because that's what an inverse is. So who's got a choice for a domain element of f? Who's got a choice for me?
0.
0 is fine. So f of 0 is 0 minus 1 over 3 minus 0. So minus 1/3. And we had this as our y-intercept anyway, right? Everybody here okay?
Yes.
Yep.
Yep. And again, if you have questions or comments in the chat, that's fine. The chat is open. So now I want to find g of negative 1/3 and see if I get my 0 back, right? So 3 times negative 1/3 plus 1. I can already see that numerator is 0 and the denominator is not 0, right? I get negative 1 plus 1 over 2/3. I get 0 over 2/3 or 0. So my input and output switched. And that's exactly what I need. But this is not good enough, right? This is not good enough for me. I can't test one input value. I can't test 100 of them. Well, I could, but it would take me forever. I certainly can't test them all. So what is our way to finally say we definitely have an inverse?
You put G as an input of F.
Good. So I want to check two compositions. F composed of G and G composed of F. And what should happen?
It should fall apart.
I like it.
Equal
Yeah,
X.
everything falls apart and all I get back is the input, right? Everything cancels out. They undo each other, right? So f, again, was x minus 1 over 3 minus x. G, our inverse, was 3x plus 1 over x plus 1. Let's see what happens if we do g composed of f. So what am I writing first? What function am I writing as the exterior part? What's the exterior here? What's the outside function?
G of x. So
G, yeah, exactly. So 3 times x plus 1 all over x plus 1, right? And now inside of that, I'm putting in the function f, right? So I'm putting in my x minus 1 over 3 minus x in each of those inputs. Nice. I have something called a complex fraction. Whenever I have complex fractions, I like to eliminate the interior denominators. Notice the interior denominators are what? Excuse me. What are my interior denominators? This is my whole denominator, right? But I'm just
3
looking.
minus 6.
Yes, I'm just looking for those interior denominators, right? And I have it twice, but it's the same, right? So I do know my common denominator, or LCD in this case, is 3 minus x. So I multiply by 1 as that LCD over itself. And I'm distributing this in. So I get 3 times x minus 1 plus 1 times 3 minus x. I'm not trying to do too much here. I'm just trying to, do a simple baby step every time just to see what happens here. So I'm going to distribute upstairs. I get a 3x minus 3 plus a 3 minus x. Distribute downstairs. Did I make a mistake there? No. Did I? No. And I see some things that will cancel. The 3's upstairs will cancel. The x's downstairs will cancel. And so what do I get? I get 2x over 2. So I get x. And that's what I wanted. I have to do both compositions. But for us, we're pretty confident that it's the correct one at this point. What should I notice about the graph of these two?
They should be reflected over a line.
Yes. Which line?
Y equals X.
Y
Nice.
equals X.
Right. What's so special about y equals x?
It
1 to 1.
reflects in the
Why is y equals x so special to us for inverse functions?
because it reflects from it. F and F reflects from Y equals X.
Give me one more time. I broke up a little bit.
F reflects from Y equals X.
To G? Okay, yes.
To G.
But why is y equals x so special? Why is that particular piece so special? And it's a dumb answer, so don't get mad at me when you hear the answer.
Because it's like really 1 to 1.
It's probably the most one-to-one. It's
You can
right.
ever
It's
get, I
yeah. It's y equals x, x equals y. It's already switched in its original form, right?
It's already A equals B.
Yes. Yeah. Once I plug in a equals b, I just have to prove that a equals b, right? So there's my original function, and here's my inverse. What was it? 3x plus 1? Is that correct? I forget it. Right? 3x plus 1?
Yeah, 3x plus 1 over 1 plus x.
Thank
or
you.
x plus 1.
Thank you. So I'm looking. It's really nice to look at right at that y equals x piece. You can see that reflection happening. Right? You can see that reflection happening really, really easily. Right? What's nice is if I put a perpendicular. Anybody know the equation of the perpendicular line to y equals x?
Is it Y equals negative X?
Nice. So I'm going to do negative x plus h. So I get a little slider here. So now I can move that perpendicular line anywhere I want. But you can see, like if I pick 2 points, like 1. What do I get when I plug into f? What do I get for 1? I get 1, 0, right?
Yeah, 1 0.
1, 0. And then when I put the switch point in 0, 1, right? And you can see I'll slide my once I slide my perpendicular, you see it's right. It's exactly opposite of it. It's a mirror from y equals x.
Right, right.
Nice. So, I mean, that's going to be an easy first question on test 3, right? Easy. I mean, it's not easy, but you know it's coming, and you know how to do everything, and you know how to double check it with a graph, right? You know how to use the calculator to your advantage, right? Cool. Great participation there. I'm very happy with the knowledge that's happening there. And if you're lost, please let me know, right? I'm supposed to be your guide. All right, let's talk about the exponential and log questions from last time, right? So this is kind of like a 5-3, 5-4 recap. It was it's one of the most boring lessons. The one coming up, like Monday, is an interesting one when we start solving equations involving exponential functions, logarithmic functions. I think that's as and I'll put it in quotes, entertaining as like the problem we just did, right? So, but this one's a little bit boring. But we just started. What was our translation, right? If we have an exponential function y equals b to the x, how does this translate? And this double arrow is logically equivalent, right? One implies the other implies the first, right? So if one leads to that, the other leads back. What's our translation?
Log b
Yes.
x equals y.
Nice. Log
Log
base
base
b
x.
of
X.
of
Of Y.
y. And because we're really kind of stressing that the inputs in my parentheses, right, are getting switched, and more so that a log function is actually a what?
An inverse.
Yes, the log function is the inverse of an exponential, but look at what log base b of y equals. What can I really be thinking about a log function as a what? What is it? What's the simplest way I could say what a log function is? What does a log function produce for me? Diego, I thought, Alan, you say that?
Inverse.
It is an inverse function, yes. Even simpler than that, right? What is this result? What is coming out of this machine? What is the result of
The exponent?
the exponent? That's what it is. A log is just simply an exponent. The result from my log expression function is the output is an exponent. And exponents are really easy, right? We've been doing exponents for a long time. 2 squared, 2 cubed, that type of thing. We understand exponential pieces. We might not quite understand logs yet, but we will very soon. So like we had a problem at the end of last class where we had a function like y equals log of x minus 3, and I wanted the domain, right? But what do we do? Does anybody have this answer? What is this domain here?
I want to say it's all real answers, all real numbers.
Okay, so it actually is a lot of them. It's not all of them. It's 3 to infinity. But we're not quite. I mean, today we're going to talk about how do you do a domain of a log function. But right now we're talking about. I don't know how to think about this in terms of logs, but I do know how to think of it in terms of exponents. So I want to convert this into an exponential equation, and then find what? Remember, my question is, what's the domain of this log function? So, but what am I going to do? I'm going to turn it into an exponential function and find what?
The vertical asymptote?
There is none in this case, but I'm going to find the range. If I find the range of the inverse function, that is the domain of the original function when they're inverses of each other, right? Okay, so what do I do here? What's my base?
10.
Nice. 10 to the what? What's the exponent here?
Y.
Thank
X
you.
minus
Thank you. Equals x minus 3. Remember, the output of the log is the exponent. I can switch x and y, right? It's not a problem.
How you got 10?
When I write a function as log, right? Remember, log of x is log base 10 of x. It's so special that we give it its own name, right? Just because of these guys here, right?
Okay.
And then ln of x is what?
The base is e.
Log base e, right? So since these two are so special to us, we just use their shortcut names. So I've got now 10 to the x equals y minus 3, right? I can switch my x and y anytime. And I solve this for y. I get y equals 10 to the x plus 3. And I know how to graph that. I have a horizontal asymptote at 3, right? And that increasing exponential function there. So what's my range here? It's from 3 to infinity. And there's my domain of the log function. That was something I actually forgot to do in the previous problem, right? Go back to that previous problem real quick. Wait a minute, where is it? Yes. Here's my function g what's the domain of G? Everything except for x equals
-1.
-1, and that was, remember, that was my range of f, right? So nice little trick. All right, so now we have a brand new domain rule. Okay, a brand new domain rule. We had only 2 so far. Can't divide by 0 until you take Calc 1, then you'll know how to divide by 0. And I can't take a square root, even root of a negative number. We're basically just dealing with square roots most of the time, right? Because then I get a complex result. I want to keep everything real. And so we have a brand new rule for our domain, our library of how do I find domains. So this is my new domain rule. If I have the function y equals log base b of f of x, I need f of x to be greater than 0. So that that inside function, whatever it is, cannot be negative, cannot be 0, right? Right? So like when I had square root of f of x, what was my domain there?
Fx cannot equal a negative number.
Right, so f of x is greater than or equal to 0 is fine, right? If I had y equals 1 over f of x, right, then I'm just making sure that f of x is not a 0, right? Right, so now, so those are my other 2 domain rules, right? Now I've got a new one. If I have a log function, I have to make sure that interior is positive. Now, look at the log graph, right? Look at the graph. So like we did 2 to the x and log base 2 of x last time, right? But look at the log graph. There's my exponential. There's my y equals x. And then here's the log graph, right? And so you can already see by the graph that there are no negative or 0 inputs for this green function, right? Right? Think about our horizontal asymptote for the exponential, right? That ha is what y equals 0 for 2 to the x, right? And what's the vertical asymptote for the green function, right?
X equals 0.
That's right. So that vertical asymptote is telling me where my leftmost of domain is, or right, you know, where that cutoff is. I certainly can't let that right be 0 there. So now why does it make sense? Why does it make sense? Now we're looking at the graph, it makes sense, but why does it make sense that log base b of anything? Why does it make sense that I can't put a 0 in here? Why does it make sense that I can't put a 0 in there or a negative in there?
Because anything to an exponent's not going to can't equal 0.
Brilliant. I didn't expect you. I was going to get ready to play cricket noises, but it's hard to think about this. If we look at the graph, it's easy, right? But what we have to do is have to translate it back into, right? We have to translate this back into b to the y equals f of x, and b to the y will never be negative. No, right? Remember my demands on my base. It has to be between 0 and 1 or bigger than 1. So it can never be 0, it can never be negative. So that's why the results of the exponential are going to demand, right, the domain of my log functions. So here comes your second question on the next test. I mean, the tests aren't easy, right? And so, but our results are not been great. So I'm trying to I can't make the material easy. I mean,
you can try.
I know I can't. I can't.
So hypothetically, what's the second question of the test?
Well, not, I mean, very, very similar. I'm going to ask you for a domain of a log function. So here it is. So find the domain of f of x using a sign table. Now, we had a question on the last test, and I said, solve this rational inequality using a sign table. And more than half of you did not even put a sign table on there. And I'm telling you, I need this. I need this for Calc 1, Calc 2. So don't fight me on it, okay? Learn how to do a sign table. You're actually going to see, usually in Calc 1, I simplify the sign table quite a bit. But I'd like you to be able to do this version of it now, okay? So here's my function. Let's do the ln of x squared minus 1 over x squared minus 4. Now you'll see when we do some of the properties today, I'm going to put restrictions on all of my factors on the interior to make things easier, so that we don't have to think about how complicated this particular problem is, right? But this is a question from 5.4, section 5.4. We're going to be doing 5.5 and 5.6 in the next two classes, including today, right? So so I want to think of this domain. Now, what's my domain rule for a log function? This is a log base e, right? Natural log ln.
If f(x) is greater than 0.
I have to make sure this interior function is greater than 0, right? So I mean, I can call this inside guy g of x if I want, right? I have to make sure g of x is greater than 0, right? And we did this already, right? This is g of x is what? X squared minus 1 over x squared minus 4, which is what? Who's got the factoring here for me?
On the top, I think it's x plus 1, x minus 1.
Nice. And then
and on the bottom, x plus 2, x minus 2.
Nice. And what I'm really thinking of doing is giving you some function that you'd need to factor with synthetic. So I could hit that piece again. Some of you had trouble with the synthetic division on test 2. Some of you had trouble with completing the square on test 1 and test 2. Right? So I'm just trying to give you more chances to show me that you can do this stuff. You can do the stuff that you need to be able to do instantly in Calc 1. Right? So we're going to go for our sign table. What are my critical values?
1 minus 1, 2 minus 2.
Beautiful. And I want to go in order, right? I want to kind of go in order because I'm going to create my number line, right, from there. I want to be thinking about them from left to right because I'm actually going to superimpose them on my number line, right? So negative 1, oops, negative 1, oops, negative 2, negative 1, 1, and 2, right? And I want all of them in open parens. Why?
Because
They can't
greater
use
than
values.
Good. Good. I heard the two things I need. I need this function to be bigger than 0. So if I let negative 1 or 1 in, it's equal to 0. No good. Can't put that into a log function. And then at plus and minus 2, I've got vertical asymptotes, right? So those are no good either. So these critical values are creating the columns to my sign table, right? And the rows are going to get created by what?
There's a zero.
The factors.
The factors of the.
Yeah.
And what else do I need to get my
Change your random number between the columns.
beautiful? I need test values left of, right of, and in between all of my criticals. So let's say -3 here. I get to pick anything. I'll do -5. I'll put -1.5, 0, 1.5, and 5. It doesn't have to be symmetrical. That's just my my issue. I want things to look nice, but it doesn't matter what you're anything in between, right? Left of, in between, and right of all the criticals. So now I'm testing this. Is everybody following here? Everyone's comfortable with this?
Yes.
Nice. I got a
It's a lot, but I'm okay.
yes. It's pretty intense. It's almost as intense as when I go camping.
I hate that.
Oh my god.
I hate that so much.
Ah.
Okay, so I'm going to test
I
the
crushed my soul.
I'm going to test the -5. It looks like I get negatives everywhere, which means my whole function is positive. So that piece of the domain I like, right? I'm already liking that particular interval, which was -infinity to -2, right? Because I need this function to be positive to be able to put it into my log function.
How do you know which function you need it to be positive or negative?
Yes. So I think who is that? I lost.
It's Michelle.
Oh, Michelle, thank you. Remember, I'm putting in the -5 to each of these functions, right? And so each of those values are negative, but you see I'm going to multiply or divide all of those numbers. And so double negatives will cancel. Is that answering your?
Yeah.
Yes. So if I have an even number of negatives, I'm going to get a positive result. If I have an odd number of negatives, I'll get a negative result.
Mm-hmm.
And we want all the positive results because g of x can't be...
Exactly. I can't put a negative or a 0 inside of a log function. So when I put the -1.5 in, I believe I get negative, positive, negative, right? So that's a negative for me. I don't want that interval. I can't put that negative inside the log function, right? Any number between -2 and -1 will give me an error. I could get low battery out of the calculator, or I could, right? I mean, can you just do that for me real quick on your calculator? ln of -1.5, ln of -1.5, and it, right? What the hell does it even say there? It says there's something wrong, right? Are you seeing that on your calculators? Oh, here come the crickets.
Yeah, error, non-real answer.
Yes. Anybody else get something similar? Anybody get low battery?
It gives me a domain error.
Mm-hmm. So the rest of this is pretty easy. When I put a 0 in, I get a positive, negative, positive, negative. So again, there's a positive interval that I want. Right? When I put the 1.5 in, I get a positive, 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 negative. Don't want that interval. And when I put the 5 in, I get all positives, so I want that interval. And the union of those is my domain, right? The domain of f is -infinity to -2, union -1 to 1, union 2 to infinity. Beautiful. So that was last class. Now, I want to look at the graph of this, okay? I want to look at this graph. So, because that's going to kind of set it in stone for me. Well, I'm a geometry person, so I want to have a visual for it. But I think even if you rather do the algebra, I think it's still a good idea to take a look at the picture and see if you can kind of connect to them, right? So let's go to Desmos here. And of course you're going to be using your calculators do you want to see me do it in the calculator, or do you mind if does anybody prefer me to use the calculator since that's what you have to use on your test?
It doesn't matter to me.
Okay, anyone?
Sure, that'd be fine.
Calculator?
Yeah.
Okay. And I mean, I guess I probably could get a better piece of software. It's just so small on the screen. That's why I don't like using this, but that's fine. So y equals, I had the natural log, right? And I have to be really careful here. I want to make sure I'm using the standard form and wrapping multi-terms, right? So I need the ln of parenthesis x squared minus 1. That was my numerator, am I right? Was it x squared minus 1 upstairs? I forget.
Yeah.
Thank you. Divided by wrapped, because I have two terms, x squared minus 4, right? And then I want to graph it. Now, this is the other piece of this particular issue here, is that we don't have great memory here. This dinosaur thing called a calculator, it's not the best for memory. So I gotta make sure that I'm using my knowledge of the asymptotes and everything to really get a better idea of this graph. I'm just going to zoom in a little bit. So zoom 2. When I zoom in, it kind of, do you see it? It's so tiny. It's blinking at the origin. Do you see it? Do you see a point blinking at the origin on my calculator?
Yeah, I see it.
Yeah. So that's, I can move that and I can zoom wherever I want, but I'm going to zoom there, zoom to the origin. And now I can see a little bit better of what's going on. And remember, I kind of have this already figured out here, right? I've got my number line, -2, -1, 1, and 2. And I know at -2 and +2, there are vertical asymptotes, right? Yes, you with me? So I'm kind of seeing, I can see some things happening. I'm kind of seeing this and this and this, right? So I get an idea of what's going on. It's not powerful enough to give me a real good picture, but I've got to have an understanding of what's going on, really. Now, this is the key here, is I want to graph the original function, and I want to graph the interior function. Okay, this is really what's going to get it to me here, where I'm really going to get an understanding. Now, that interior function, and I could have done this nicer, but it's okay. X squared minus 1 close divided by open x squared minus 4. Remember what that interior function is, and now I got to zoom out again. Sorry, I want to zoom standard again. Zoom 6.
So did you add a function there?
Yeah, I put the whole function, the ln function, and then I also graphed the interior function. Remember, the interior function is what I used to find out. I'm asking for that interior function to be over the x-axis, right? So you could see that little piece on the left is above the x-axis. That piece on the right is above the x-axis. Look at the piece in the middle, right? Let me zoom again. Zoom 2, enter. Look at the piece right. So there's the ln function being graphed. And now watch this piece in the middle. Do you see where it's above the ground? Do you see where it went above? It went from -1 to 1.
Value.
Exactly.
Okay.
right? So that second graph was the graph of this, right? Where was that G above the ground? From there to there, then from there to there, then from there to there, right? So that's where the G was positive, and that's what I could put into the log function. Okay, all right, we're ready to move on. New stuff. I don't think I'm going to get this all done today, but you got some homework to do. You got, right, I forget which homework numbers they were, but it's 5.1, 5.2, 5.3, 5.4, right? Some of you probably didn't do the sign table homework in chapter 4. That's 4.6. So get to work. Okay, here we go. New stuff. This particular lesson is very simple, but it's like, what? You're gonna see it and you're gonna go, what the hell? And so you gotta kind of, there's times in life that you need to adopt blindly, accept things before the understanding comes. And this is, I think, one of those things. I will try and prove these things to you, but the proofs might not even make sense to you. Actually, they're not difficult at all. But then just using them is going to really be the key, right? Like using a car, you don't really have to understand how a car works to use it. I mean, it will help you get better gas mileage, but so we're just going to adopt these things and use them, right? And so we're talking here today about properties of logarithms. Properties of logs. And there's a whole bunch. I like to say even our translation is a property. Then we're going to have products and quotients, inverse properties, and change of base. So we have a whole bunch of them. I don't think I'll get to all of them today, but I'll finish it Monday, right? So I want to have this translation, right? So b to the x equals y is equivalent to what? Log base b of y equals x, right? So I want to have that translation. That's the book doesn't call that one of the properties, but I'm saying I want to think of these properties as just these unique characters of what we're doing, or kind of idea, subtleties, or I don't know. But so the translation we already knew. The next one are products and differences. Sorry, products and quotients. And so this one is, if I have log base b of m times n, I get log base b of m plus log base b of n. So this is just a particular interesting aspect of log functions, that when you're multiplying in the argument, you can split it into the sum of logs, right? Now that one, it kind of should make sense because we know what a log is, right? We know what the result of a log function is, right? What is the result of a log function?
An exponent.
Exponent. Okay. So what am I doing on the right-hand side there?
You're adding exponents.
Adding exponents. Okay. When am I allowed to add exponents?
When you multiply.
Like
They have the
when
same
you
base.
multiply like bases. Exactly. So this one should make sense. The next one should make sense. And I'll prove the first one. If I'm doing a quotient, then I'm going to subtract the exponents. And then this last one, very, very useful. Says that log base b of m to the n is n times log base b of m. So the first two we kind of instinctively get already. Multiplying like bases, I'm adding exponents. Dividing like bases, I'm subtracting exponents. This one, I want us to have a way to say this, right? The exponent of the argument, right? The exponent of that input, right, becomes what?
The multiplier.
Sure, coefficient. Multiplier, coefficient. Yeah, absolutely. And so that's, I just want, right? So we have three little kind of things that are going to help us remember what the hell's going on here, right? Even though we haven't seen a problem yet, adding exponents, subtracting exponents, and then my exponent becoming a coefficient, right? Exponent of the argument becomes a coefficient, okay? So, I want to prove the first one, and maybe I'll do a subtle proof of the last one. I am going to run out of time here. You're not going to be able to get to this homework, but that's fine. You don't mind that, right? You've got other things to do. So I want to prove the first one, okay? Oh, and by the way, I've got more properties to talk about, but I'm not going to get to them. But I've got the inverse properties. And I've got change of base. So kind of a collection of four groups, right? Inverse properties, I'm really going to be talking about two of those, change of base, two or three of those, and then these products and quotients. So let's see if I can prove that first one there. And you're going to help me, okay? So log base b of a product n m times n should be log base. This is what we're trying to prove. Log base b of m plus log base b of n. So those are kind of complicated, so I just want to rename them all something, right? So I'll use capital letters. I'll say this is A and this is B plus C. So if I can prove that A equals B plus C, I've got this thing proved. But I have no idea what to do for this thing. Anybody have an idea?
Pick two random numbers.
Yes, so the problem with picking random numbers is that I can't pick every random number, right? I can't pick every combination of two random numbers. So it might work in one instance, but not a proof. So I want to do something more general. Anybody have an idea? It's on the page that we're looking at. Let me get my crickets here. Give me a second.
Oh no.
Professor, are you asking us to pick the random values?
No, random values isn't good enough, right? Like, remember when we were doing the inverses and we picked something in the domain and it worked? But I can't do it. I can't prove things that way. It's a good way to disprove something. If you can find two values where it doesn't work, that's a great way to disprove something, right? But sometimes that's very hard, right? Like every living unicorn has two horns is impossible to disprove because you can't find me a living unicorn, right? Anybody, it's on the page and it's in a blue box.
inverse.
Use the translation. Use the translation. So what am I really saying here, right? What am I really saying here is that log base, so this is my left-hand side, right? I'm saying log base b of m times n is a. I want to translate that to what? What's the base?
6.
B, right? So b to the what?
To the
A.
Yes,
A.
b to the capital A equals m times n. I'm going to do that on the right-hand side as well, right? Maybe I can just go to the right-hand side pieces. I don't know if you can think of that. Can you give me the right-hand side piece without? What's the base? So I'm looking at this part now, right? I'm looking at what's the base?
B to the
Yep, lowercase b to the capital
lowercase b to the capital B
equals
M.
m. Nice. And then the last one is lowercase b to the capital C equals n.
Yep.
Everybody with me?
yes.
Anybody? You know, and if you're a little lost here, it's understandable. It's like I'm proving something, but I don't care. I don't care so much of the proof as much as I care of the application of the property, using the property, which I haven't seen yet. So you just gotta be patient with me. I'm scrambling for time here. All right. So it looks like I have something nice I can put together here. On the left-hand side, I have an m times n. And on the right side, I have an m times n. Right? M times n. So left-hand side, what is it? It's b to the a, right? And on the right-hand side, it's b to the capital B times b to the capital C. Right? You see that? I took this m times n, that's my left side, and I took this m times n, and that's my right side.
Right, and now you can just add the x.
Now I'm multiplying like bases. So b to the capital A equals b to the capital B plus capital C. But an exponential function has what special property? What do I know about exponential functions? What do I know about exponential functions?
It can't equal 0. It can't be negative.
Good. What else?
Then they can't be negative.
Yes, I agree. What else, though? What other thing do you notice just by looking at the graph of this exponential? What do you notice about it?
Increasing.
Good. What else? Good, Alan. Thank you.
It's 1 to 1.
1 to 1. So I have equal outputs. I have equal outputs now, which means I must have this
Equal inputs.
Equal inputs. So A must be equal to B plus C. There it is. Now let's just look at a quick Math Excel problem.
Wait, so
Diego, go ahead.
what were we doing?
Trying to prove that this particular property is true.
Okay.
Yeah. Let's look at a real simple example, okay? So let's look at log base 2 of 2 times 8. Okay, so of course that's log base 2 of 16, right? Yes? But I want to use my property here to split this into 2 logs. So we're going to write what? Log base 2 of what?
2.
Yep, of 2 plus log base 2 of 8. Yep. Now I'm saying we know all of these answers. I'm asking you to think in terms of logs now, right? And the old joke is if you're doing a log problem in the forest and no one else is it. No, I don't know. It does not, you know, I'm still working on that joke. So on the left, though, remember what a log is. It's the exponent. I need the exponent of 2 that will give me 16. What is the exponent of 2 that will give me 16?
4.
Yep.
4,
Yep. What is the exponent of 2 that will give me 2?
1,
What is the exponent of 2 that will give me 8?
3.
30.
Uh-oh, it looks like it worked. So, I mean, it's a real silly example, but, right, you're just trying to get a grasp on this particular thing. Why are we doing these properties? You're going to see when we do the equations, when we start solving equations. So I need these properties to be able to manipulate equations in order to solve them. So, but first we just give you the properties and ask you to practice with them. So it's kind of silly, but let me look at it. Do I have time? Yes. I want to take a quick look at a homework problem in this section. And again, you're not going to be able to do all of it. You could do some of it, but you would go to that homework and you start reading about change of base. I'm not getting to change of base today. You certainly can read ahead for me so that when I do change of base, I can do that a little quicker. Oh my God, it's slow. It's like how many buttons do you have to click to get to somewhere? In Math Excel, it's horrible. I'm not supposed to say that, I guess.
So many. You have to go back to some. You can't just go back to the last page.
I know.
It's a pain in the end.
I know it is. Sometimes you just have to give in, Joe.
I refuse to accept such a shitty software.
It doesn't get any better as you move. I'm telling you, none of the software is ideal. None of it. I know you said you're friends with Alex. I can't stand Alex, but so I mean, this is the very first problem. It's very simple, but obviously I'm multiplying 36 and x in the argument. Yes. So log base 6 of 36x. So I want to use, and the homework says, use the properties to simplify this, right? So log base 6 of 36x. So obviously I'm multiplying, so I'm going to split it into 2, right? And then I want to see if I can simplify anything else, right? So, but I do know what exponent makes 6 into 36, right? So I get 2 plus log base 6 of x. And it's hard to argue that one of these is any simpler than the other, but we need you to be able to use this property for what's coming up, okay? And in fact, even for limits in Calc 1, right, which is Chapter 2 in Calc 1, right? I do a bunch of limits using properties of exponents and logs and derivatives. That's Chapter 3. So we just got to practice. That's all. It seems very strange. I agree, right? I mean, at least I think you are probably going through what I went through when I started doing these. I'm like, what the hell is this? Here's one. Let's do ln of x over e to the 6x. ln of x over e to the 6x. Now I got another property that's going to come into play here. So, and I didn't really prove that one yet, but we'll see what happens when we get here. So first of all, I can see I'm dividing, right? So I get ln of x minus ln of e to the 6x. And I had this property that if I have an exponent of the argument, right, if I have an exponent of the argument, that exponent can come out front as a multiplier, right? ln of x minus 6x ln of e. And what is ln of e? You can do it on your calculator for me. What's ln of e?
1.
1. So I get ln of x minus 6x. And I like to wrap that argument at times so it's not, sometimes it could look a little confusing just to have ln of x and not show that it's the input of a function. But of course both would be right. ln of x minus 6x. MathExcel would take that for sure. I have no time left, so I'll prove that last property next class, and then we'll finish the list of properties. Okay? So have a great weekend. I'll stick around if yes, Alejandro. Yes, exactly. Subtracting because we're dividing. Exactly. So have a good weekend.
Thank you.
See you
Have a good
Monday.
day.
Thank
Have
you.
a good one, Professor.
Thank
Hi,
you.
Professor.
Thank you, Professor.
Thank you, Professor. Have a good one.
Thank you too.